It's constant.
All right. May I have your attention? I would like actually to answer what is an inertial reference frame one more time, because very often when students write what is an inertial reference frame, they say that it is a reference frame in which object has zero acceleration, which is wrong. Objects, I mean, that way your reference frame is all, I mean, if you think about yourself, how fast well, what is your acceleration in your reference frame? Zero, right? You never move in your reference frame. Well, is your reference frame then an inertial reference frame? No, not mentioning that if one object has zero acceleration doesn't mean that another object has a zero acceleration, right? So, important thing is that you have to pick a particular object, and a particular object will not have will have zero acceleration. What object you have to observe in order to verify if a reference frame is inertial or not? You have to find an object so that you recognize that that it does not interact with anything else. Well, to find such an object is a hard task, because if we look around ourselves, we always find that Earth is interacting with that. From the configuration, we are too close to Earth, and even if we think about Earth, well, then there is sun in the vicinity. There is always a problem. I mean, really, if you want to find an object, you can probably find only one object in the universe that you know that it doesn't interact with the rest of the universe. What is that object? A what? Why not star is not interacting with Andromeda galaxy? You don't know. Yeah, or with actually even with the Earth. No, North Star is not the one which does not interact with the rest of the universe. It's hard to find. Well, I tell you what is that object. The entire universe. Yeah, outside of the universe we have nothing, so the entire universe does not interact with the rest. So the reference frame of the universe, well, actually we don't know where to find origin. Later on, when we study a little bit more of physics, we will recognize that definitely picking the center of mass of the universe would be a good place to choose as the reference point. Well, but then there is another problem about rotation, how fast we have to rotate. I mean, how fast that reference frame has to rotate. Problem is that I mean, if all the stellar objects had fixed positions with respect to each other, then we could choose a axis in such a way that they are all still. Then it would be good, but this is not the case in the universe. Well, we will learn in the future that a certain physical quantity called angular momentum, and if we believe in Big Bang and conservation of angular momentum, we would have to choose axis in such a way that the total angular momentum of the universe is going to be a zero vector. So this is an inertial reference frame. And actually, because of Galilean transformation, we saw that if acceleration in one reference frame is zero, then has certain value, then acceleration in another reference frame, which is related through Galilean transformation with that first reference frame, has the same value. So any reference frame related to through Galilean transformation with the one which I just specified is also inertial reference frame. Now, what is the requirement for Galilean transformation? It is that reference frame has to move with a constant velocity in that first one, and it should not rotate. And so the axes remain parallel all the time. All right, so we can actually find a lot of inertial reference frames in the universe. We can even find, in principle, an inertial reference frame which has origin at this point. It has to rotate appropriately and fly with a constant velocity through in that other reference frame. All right. Now, obviously, when you construct something, you are not going to reference it to this reference frame. We just can find other reference frames, and for engineering purposes, reference frame of the ground is good. So reference frame of the classroom is approximately inertial. It is almost inertial. It's not exactly inertial, and unless you are a weatherman or you serve in the army in artillery, then you wouldn't care that reference frame of the ground is just approximately inertial. Weatherman and army recognizes that the reference frame of the Earth is not. Actually, with the army, it is that only during World War I was the first time that army noticed non-inertiality of the ground reference frame when it is that when humanity developed super guns. And German had a super gun, Big Bertha, which had a range of, well, about 50 kilometers. And on that distance, they were already missing targets because of non-inertiality of the reference frame of Earth. Now, if you are a weatherman, actually, it would be very important to recognize that the non-inertiality of our reference frame, because certain phenomena in the atmosphere happen because of that non-inertiality. Do you know what? Anybody? Wind pressure. I mean, you have to be a little bit more specific about wind and pressure. What something indeed which is associated with wind. These are particular winds. A what? No. Tornadoes. I'm not sure about tornadoes. I will have to check it actually. A what? Hurricanes. Correct. Hurricanes, the reason actually that hurricanes on the northern hemisphere, if you look from the top, on the northern hemisphere they will rotate counterclockwise. On the southern hemisphere they will rotate, on the northern counterclockwise, on southern clockwise. Also trade winds. They are associated with non-inertiality of the reference frame. Fact actually that the masses of Earth turn sideways results from non-inertiality of a reference frame. But any type of constructions of building, roads, bridges, motion of pieces of machinery can be properly analyzed and described in a reference frame of a classroom, of a reference frame of the road, and so on. All right. Now, how to test that actually? Because we can think about something how to test if this particular reference frame is inertial. Obviously, we cannot isolate an object from interaction, because really the way to do it, we would have to bring an object here, make sure that it does not interact with anything, and see if it is going to stay in place. For example, important thing is that it does not accelerate. We will never get rid of gravitational interaction, so it's difficult to do. So we can actually make it a little bit weaker, and if we make sure that all the forces exerted on this object cancel each other out, So the result is like there were no force exerted on that object, then this object should have a zero acceleration as well. If we can test that, then we recognize that the reference frame is an inertial reference frame. Do you understand that? So remember that inertial reference frame is not the one in which an object has a zero acceleration. It is that if an object does not interact with other objects, or if you recognize that the resultant force exerted on that object is a zero vector, that object should not accelerate. All right, and only in inertial reference frames, acceleration and net force are directly related. Only in inertial reference frame, acceleration is proportional to the force. In non-inertial reference frames, objects accelerate without interaction, for no reason. Sometimes even can happen that it's the other way around, that it is obvious that there is a force exerted on an object and the net force is not zero and the object does not accelerate in this reference frame. It can happen as well. All right, so now we have to learn how, from looking at the configuration around the object, we can recognize how the object interacts. We will have to learn about interactions. Well, fortunately, there are very few of them, which you will have to make sure that you recognize those few and don't create more, because I bet that as the classroom you could double the number of interaction in the nature right now. You will come up with ideas for interactions which do not exist. All right. In nature, actually, there are four on the microscopic level. So forces between atoms. Well, no, particles constituting matter. So it's not only between atoms, but even within nucleus. There are only four of them. In other words, nature produced only four forces. Einstein was actually working on the theory for which he would develop a single formula for all forces. He wanted to recognize that there's only one force. He failed to do that, though. Anyway, so there is gravitational interaction. And I will talk about gravitational interaction today. We will learn about gravitational interaction today and how to recognize what is the value of what is the force associated with this interaction. This will be subject of physics 2 now. Electromagnetic interaction. Electromagnetic interaction is, for example, responsible for northern lights. We will not even discuss the next two. There is a strong interaction which holds nuclei together. And those of you who know, for example, how nucleus of helium looks like, well, it has two positively charged protons and two neutral neutrons. So if we consider just gravitational and electromagnetic interaction, the nucleus has no way to stick together. It has to fall apart. Strong interaction actually holds it. There is a weak interaction which actually causes that from time to time beta particles fly away from nuclei. All right. Now, as engineers, obviously you don't have every time to draw a free body diagram going to including these forces. It would be too complicated, because if you wanted to draw a free body diagram just for me, for every atom in my body, you will have to consider interaction. Well, so in engineering, actually, we introduce non-fundamental forces, which result only from those four. And this is which we have to learn how to recognize. All right. So first, let's say gravity. And I even brought here, I mean, right now I want actually to bring out a sequence of events in our history which led to gravity. Because before gravity was identified as a humanity, we already were aware of Saturn force. Ancient Greeks actually found it, noticed it, and well, they noticed it actually that certain stones called amber produce that force. Do you know what force I'm talking about? I mean, we experience that force also quite often. Electrostatic interaction, correct. So electrostatic interaction was noticed before gravity, and actually there was a time that we thought, then when we already recognized that Earth is round and that Australians walk upside down, so how is it that we stick to this ball called Earth? We thought that it is also the same way as pieces of matter stick to amber, that it was electrostatically. All right, now when we will talk about electrostatics, we will see a major difference between gravity and electrostatics. Right now I don't want to talk about that. How about if I talk about gravity, which actually leads also to a question. We know what is the mass of the Earth. Yeah, if you flip your textbook, you can find out what is the mass of the of Earth. Well, how did we figure it out? Well, one of the way probably would be to take a stone and see what is the density of that stone, and we could measure how big is Earth. We can do that, right? Because we can see how direction changes as we walk on the Earth, or how far is to the horizon. From that we can figure out what is the radius of the Earth, so we would be able to geometrically to determine the volume of the Earth. And if we know density of the stone, probably we could figure out mass of the Earth. But there's a certain problem here. What? Correct. Yeah, we couldn't just multiply density by volume. We will have to integrate density over entire volume of the Earth, and we don't know how density varies. So this was good. I mean, maybe even today we could find some kind of technology to do that, because we know what is where. However, the time when gravity was developed, we didn't have technology. So how to weigh the Earth? And well, it's a sequence actually of events and very number of scientists who contributed to that. Well, I would like to bring Copernicus as the first person who actually gave an idea to complete this task, to discover gravity and to weigh Earth. And what Copernicus did, I mean, actually he noticed an inertial reference frame. Yeah, because before him, we believed that Earth is the center of the universe and everything turns around, moves around, entire universe moves around the Earth. Well, at that time we didn't know Newton's second law, so there was no problem that some planets, well, I mean some objects, which we called planets, moved along a strange path for no reason. We couldn't figure out actually, because I mean we believed already that there is a push or pull needed to change the motion without even knowing really that it's force. So, not mentioning that those motions were pretty complicated. So Copernicus actually decided, well, suggested, well, why not to put origin on the sun? Then the motion looks much simpler. All objects, all planets now move in almost circular paths. Those paths are called orbits. Yeah, so he invented heliocentric system, which is actually more inertial than the reference frame of the Earth. Oh, astronomers! I mean, this is another group. So in adding to which we would have to the weathermen and the army. For astronomers also recognize non-inertiality of the Earth's reference frame. All right, now Galileo, I already mentioned that he was actually studying how objects move in the vicinity of the Earth, and he recognized that well, the rate at which these objects move does not depend on the mass. It doesn't matter if we throw from that Pisa tower, if we throw let's say a stone or a computer screen. They will fall at the same time. They will move with the same, well, we know that they move with the same acceleration. He didn't have concept of acceleration yet. He actually made one more important invention. He created, he had another invention. Okay, so he studied motion. He also constructed a telescope. So another guy called Johannes Kepler took this telescope and started to stare into space. Well, at a certain point he looked at Jupiter, and Jupiter has several moons, and those moons move relatively. I mean, the month on those moons is much shorter than the month on, but that didn't matter. He was able to observe motion of the moons. And he recognized that the square of the time which moon requires to orbit the planet is proportional to the third power of the radius of the orbit. Well, this fact, when Newton already invented his laws and related motion with acceleration, he predicted that the force which holds those moons on the orbit, well, has to be inversely proportional to the square of the distance. If it is inversely proportional to the square of the distance, then we will have this relationship between the radius of the orbit and time along which, I mean, time required to complete the orbit. Now, so really, actually, Newton combined already several facts. In order to have such a relationship, force should be inversely proportional to the square of the distance. Galileo already recognized that objects fall independently of the mass, so Newton also concluded that that force must be proportional to the mass of the object. So he figured out, he came to the conclusion that the force which holds those moons has to be proportional to the mass of the moon. Well, if it is proportional to mass of the moon, then we can recognize that symmetry requires that it must be also proportional to the mass of the planet, because now Newton's third law, his third law says that there is a symmetry of that interaction. And this is how far Newton actually could go. He recognized that the gravitational force is proportional to mass of the planet, mass of the moon, and square of the distance between their centers. And well, he just picked this proportionality constant, which he has not determined. He didn't know what is gravitational constant. He only knew that this must be true. Well, so right now we still cannot determine what is the weight of the Earth, because without knowing gravitation, I mean, if we knew that, if we knew gravitational constant, then see what we would need to measure the mass of the Earth. We'll just have to get on the scale. If you get on the scale, right, you will determine what is the force, gravitational force exerted by the Earth. Well, you knew the radius of the Earth, so the distance from you to the center, right? Do you see that? You knew your mass, you can determine your mass. If you knew gravitational constant, the only thing which was missing is the mass of the Earth. Do you see that? Yes, so just by weighing yourself, you simultaneously weigh the Earth, provided that you know what is the value of gravitational constant. Well, Henry Cavendish, who actually lived about 100 years after Newton, finally performed the experiment developed experiment in which he was able to determine what is the gravitational force of the Earth. And really, when he did, he made a very sensitive balance called torsion balance. So he attached two spheres on a thread, so they were able to, they could rotate, and then he put two bigger spheres next to these, and really saw how that torsion balance is turned. From that, he figured out really what was the force exerted between these two. The force is tiny, but it was enough to determine the gravitational constant. All right, so after that, it was about 100 years after Newton, we finally, as humanity, were able to describe gravitational interaction and finish the formula which was invented by Newton. Very often, this formula is referred to as Newton's universal law of gravitation. Don't think that this is fourth Newton's law, because it's something completely different. The others say how to link interaction with motion. This one describes a particular interaction called gravity. All right, now we have to, I know that we already have the, well, we agreed on the convention, but I know that a lot of you are using it still loosely, so I want now to explain what is what of what over here. And to be consistent with the book, the subscripts, so if you have subscript 1, 2, it means that it is force exerted by particle 1 on particle 2, I think. Correct. So here we have gravitational force exerted by particle 1 on particle 2 is, well, its orientation, since we have minus over here, it means that it is opposite to this vector. Can you help me to comprehend the meaning of this symbol? What vector? What is that vector? Is this vector the same as this one? No. Very good. It's not the same. Yeah. Over here, this vector. I mean, let's say in English, what this vector represents. What is that vector?
It's not a vector.
No, it is. I mean, it's an arrow from here to here. And I use bold letter, so I did not put an arrow, but it's a bold letter. Yes, Colby?
Position of the second particle in reference to the first one.
Correct. This vector represents position of the second particle with respect to with respect to the first particle. So what is this vector then? Yes, Colby?
The force exerted.
No. I'm talking just about one factor. That one. R hat 1, 2. What is that? It's the unit vector. Correct. It's a unit vector. Which unit vector? It's a unit vector of vector in the direction of vector R1, 2. So it is a unit vector heading from particle 1 toward particle 2. All right. Now, this expression over here is a vector or a number? Number. Everything here, all quantities over here are scalars. So this is a number. Now, it happens that all numbers are positive. Therefore, this entire number here is negative, which means that this force is opposite in direction to this unit vector. So since unit vector is from particle 1 toward particle 2, the gravitational force is heading toward particle 1. Now, which gravitational force? Exerted by particle 1 on particle 2. All right. Now, just to recognize that we are talking about force, we have to answer ourselves those three questions. What does this symbol represent? If it represents a force, we have to answer those three questions. What three questions? What exerts the force? Correct. Target object, on what the force is exerted. And the third one is what type of interaction. Can you help me with that? Can you answer these? So what exerts the force? What exerts this force? Particle 1, correct. On what the force is exerted? Particle 2. What is the type of interaction? Gravity, correct, or gravitational interaction, correct, good. Well, it happens. I mean, we are not going to do to go through the calculation, but if objects have a spherical symmetry, we can also use the same formula to describe interaction between those objects. So, however, the distance should be understood that it is not the distance from surface of one to the surface of the other, but from the center of one to the center of the other. Also, if an object is small, we can consider that it's a particle and still use this expression. So, for example, we can use this expression to determine gravitational force exerted on us by the Earth. Why? Because Earth is spherical and we are tiny. So, let's say if we use this formula to determine the force exerted on me, what would I take here? This would be gravitational constant. It's just a universal constant which you have on the back of the chapter of the book, on the cover of the book. And it's fixed. Only Q on Star Trek Next Generation is capable to change it. We are not. All right. What would be M1? It is the whatever exerts a force on us. It would be mass of the Earth. Now this would be my mass, correct? What should be this distance here? Radius of the Earth, right? We are so tiny. I'm so tiny that it doesn't matter actually if you measure distance from the center of the Earth to the bottom of my feet, or from the center to the top of my head. It's practically the same distance. All right. Now, how about this vector? What will be the direction? What will be this unit vector? from the center toward me, right? So if I draw this vector next to me over here, what should be how should I draw it? Straight up, correct? So on the Earth, this vector is going to be straight up everywhere on the Earth, right? Do you see that? Which means that the gravitational force is always straight down, right? Also, always toward the center of the Earth. And this is why Australians still can walk on it. All right. In principle, actually, I could go to another type of interaction, but I still wanted actually to talk a little bit about gravity, and because it is often described, well, the interaction, and it happens actually not only for gravity, but all of those forces, or all those non-interactions which are referred to as non-contact interactions. Because gravitational force is exerted no matter if I'm standing, if I touch the surface or not. I can fly. The moon is flying far, far away, and the Earth is still exerting a gravitational force. I mean, on the other hand, it also doesn't, there's another imprecision, because in principle, you cannot touch anything. It is that if no matter how strong I squeeze my hands, the atoms don't touch each other. There is always a certain distance between atoms of this hand and atoms of that hand. So actually, in principle, we could say that there are no contact interactions at all. But if we can bring it close, we say that it's a contact force. If in our common sense the surfaces are touching, then we say that the interaction, it's a contact interaction. If the surfaces of objects are sufficiently apart that we can get in between, then we say that it's non-contact interaction. And if we have non-contact interactions, we can introduce a concept which is referred to as a force field. So for example, for gravity, we can have gravitational field, and word field actually has a double meaning too. One is that it is a space in which particular interaction occurs. So for example, gravitational field of the Earth would be space in the vicinity of the Earth, that whenever objects get into that space, it will be affected by gravity of Earth. It will feel gravity of Earth. Its motion will be affected by gravity of Earth. So for example, if you think about space voyages, you can escape a field, gravitational field of Earth. What it would mean? Get to a place where Earth already has insignificant influence, because actually everywhere in principle it will produce that field. So one meaning of a word field is that it is a space. Now the other meaning, and this is the one which I want to bring it in here, is a quantity, physical quantity, which describes this property of the space. And it is defined in such a way that, and just to make sure that I distinguish it at least for a moment between field as the space, I will call it field vector. Although in the book you don't have vector, you just have a physical quantity, gravitational field. And the purpose of gravitational field is to describe gravitational field. Precisely what I said is that we use gravitational field vector to describe gravitational field. And to each point in space, we assign a field vector, gravitational field vector, in a particular way. I'll put the subscript F over here, because I mean, when I woke up this morning, I figured out that I want to change actually this formula so that you don't confuse G. although, well, so in the book actually you don't have the subscript F, you have it written just as G. Traditionally we use symbol G as the symbol to represent gravitational field vector. All right, so this vector is defined in such a way that if we place an object with mass m at a location where the gravitational field vector has this value, then we have to multiply mass and that field vector to get the force exerted on that object. Do you understand me? Right, so for example, at this point, there is, we have, this point belongs to the gravitational field, which means that at this point we have a certain gravitational field vector. A certain gravitational field vector is assigned to this point. And it is assigned as in such a way. It exists over here no matter if there is something or not. But if I put an object over here, I have to multiply this vector assigned to that point by mass of this object to get what? The gravitational force. Which one? Exerted by the Earth on that object. Gravitational force exerted on the object. Right? So see what Earth does. Earth creates the field. By doing it, it creates a vector at each point of space. Now, if you look at space, when you walk, I want you to see those arrows downward. It's a jungle of arrows. At each point, you have an arrow. Do you see it? Mm-hmm. Great. Now, if something is there, you can figure out the force exerted. You have to take the arrow and multiply by the mass. Earth is determining properties of the field. Yes, so we find force by taking attribute of an object. What attribute of an object? Mass, correct, and multiply by characteristic of the field. What do we call it? What?
Gravity.
Not gravity. Not gravitational force. What vector? Correct. Gravitational field vector. Correct. What is mass, by the way? It describes what? No, it does not describe how much object weighs. It does not describe the force of gravity. Not the amount of object. Very good. Object's resistance to change in motion. All right. In other words, what do we call that property? The resistance to change in motion. Inertia, correct. Right. Mass describes inertia. Well, it's coincidence actually that gravity is related to that inertial property, but it happens to be. All right. Now, so if we take a look at the Earth and consider universal universal law of gravity, I can recognize that gravitational field vector at a distance, a certain distance, is opposite to gravitational constant multiplied by mass of the planet divided by the distance from the center of the planet toward the point of interest, and it's vertical. So around Earth, gravitational field vector is always toward the Earth. Now on Earth, well, let's take a look at the units. Well, force is measured in newtons. Mass is measured in kilograms. So what should be the unit of the gravitational field vector? Newton per kilogram. Now I want you actually to take a look, a closer look at when we have a certain coincidence. Newton, well, if we take a look at Newton's second law, right? So Newton must be equal to unit of mass multiplied by unit of acceleration. What is the unit of mass? Kilogram. Unit of acceleration? Meters per second square, right? Which means that Newton is the same as kilogram meter per second square. All right. If I put here kilogram meter per second square, kilogram and kilogram cancels, and it will happen that Newton per kilogram is actually the same as meter per second square. All right, and we will talk about it tomorrow. No, Monday.